Hi there and welcome to this video for Senior Physics on electromagnetism and electricity. In this video we're going to explore electromagnetic induction, or principally Faraday's Law. Now Faraday's Law basically works on the principle that induction is where a magnet is made to produce a flowing electric current as the result of an induced EMF, or Electro Motive Force. Now basically this works opposite to the motor principle. And the motor principle works on the idea that if we get a moving charge going through a magnet, the two magnetic fields which are generated, one from the magnet and one from the moving charge, will interact to produce a force and produce kinetic energy. Well, in electromagnetic induction, it works in the opposite direction. In this case, what's happening is we use kinetic energy, which means that we've got charge which is moving within a magnetic field. There's our two magnetic fields which interact. But the force in this case is not producing kinetic energy to move the wire. In this case, it's using kinetic energy to move the electrons through the wire. So we've got motion of electrons, electromotive, and it's produced by a force. Obviously, the greater the force, the more motion we're going to get of our electrons. Now remember, electrons have a standard charge, 1.69 times 10 to the negative 19 coulombs, so that's a constant, but the force will vary depending on a variety of different things. Now another name for EMF is voltage, because it's the amount of energy which is going to be given to those electrons. Now the principal thing to understand about electrons is they're all negative. Now if you know anything about negativity, they generate electric fields. Now, if I push electrons down to one end of a conducting rod, for example, in the picture here, you can see we've got motion of the wire, and the electrons are pushed down to the bottom of the rod, leaving a space at the top. Now, that space is actually called our positive end. It actually doesn't exist as positive particles. There's no positive particles there. All we have is a void of electrons. So we have a high density down the bottom and very little at the top. Now remember, down the bottom, those electric fields of those electrons are going to interact. They're going to interact and push together, and the result is they're going to want to spring away. The reason they can't spring away is because the electromotive force generated by the interaction of the magnetic fields is pushing it down in that direction, so they don't move. As soon as I release that force, they'll move back so that they're equally spaced. Remember, in nature, everything wants to be equally spaced. So what electromagnetic induction does is allow us to look at this apply this interaction of these magnetic fields to generate a current. So as I've stated, it works on the principle of moving a wire through a magnetic field. Now obviously if you've got a conducting rod such as copper, it's got free flowing electrons. Now moving that wire or conducting rod basically has got charges. Those charges are moving, and if we remember back right at the beginning of this unit, any charge that moves will generate a magnetic field. As long as we're moving it through a stationary magnetic field, those two fields will interact to produce the force. So this is basically shown in this bullet point here. If charge Q moves through a magnetic field, if charge Q moves, a magnetic field is produced. This interacts with the permanent magnet's field and as a result produces a force. This is the EMF which is going to be generated on those electrons, pushing them down one end. This force, as I state, can increase or decrease depending on a variety of variables. As I stated, that this EMF, or electromotive force, is also termed voltage. The flow of the charge is called current. Remember, current is basically the amount of charge moving past a specific point per second, okay, or C over I. So obviously if we've got lots of charge moving, then we have lots of current. Now in this case, let's not take into account the idea of resistance, because that's going to change the current. All we're working on is the principle that the electrons are given energy to one end, they may be massed at one end, and that result is that they've got specific energy. The degree with which they can flow from one end to another is going to be termed the current. Now, obviously, if the current, the conductor stops moving, then the result is that no force will be generated because we've got one of our magnetic fields has disappeared. Because that field has disappeared, there's no interaction, no force, that's it. So as a result, the electrons stay where they are. So as soon as a conductor stops moving through a magnetic field, that's it. Okay, now this was first observed, and the theories put forward were done by Michael Faraday, and as a result it was termed Faraday's Law. Now, this law, I think, is probably one of the greatest laws, or one of the greatest laws that physics has produced over time. And if you think about how much it's now used in our society to generate electricity, this very, very simple law has actually resulted in us being using this all the time. You think about any production of electricity, it's going to use the movement of a magnet within a coil, and as a result, that is where all our electricity comes from. So Michael Faraday really, in my opinion, is probably one of those greatest scientists around, because his principles are used every single day of virtually most humans' lives. So it's a huge contribution to science. And this is why I think it's one of those things that physicists really need to, physics students really need to get a grasp of and think of, how wonderful this is. It's still acting today. We're still using this principle every single day. Okay, so how do we determine the force that is applied, or the direction of the force which is applied on the electrons? Well, we can use our left-hand slap rule. Now it's left-hand, remember, because it's electrons, they're negatively charged. So here I've got my hands, and we'll just revisit this rule. Now the thumb in this case is going to be the movement of our conductor. Our fingers are going to be the direction of the magnetic field, and our palm is going to be the force on the electrons and the direction of the current. So let's say I've got this pencil here, and I've got a magnetic field running top to bottom. If I move my conductor through the magnetic field, it's going to be cutting those field lines generated by the magnet's field. So my thumb is going to be moving with the conductor. My fingers are going to be moving in the direction of the magnetic field, the stationary magnetic field. The result is that a force is going to be generated down this side of my magnetic field. Okay, so hopefully that makes sense. Now, if we were to use our slap rules, we could use a left-hand slap rule. This is the direction of motion. The result is our charge is going this way. The result that we then get is that the field lines on this end of the conductor will be going in the same direction as the magnet's magnetic field, and they'll be cancelling out on this side. The result is there's your electromotive force pushing the electrons down this end. Likewise, if it's coming back out, I'm coming back out again, the result is they're pushed in the opposite direction. So I can push this way and push the electrons down to this end, or I can pull it back out and the result is they'll come to this end. If I leave it stationary, there's no moving charge. No moving charge means no magnetic field which is generated down here, which means no push, no EMF, no current. Okay, now the size of the EMF can be increased by a variety of different features. Now this diagram on the right hand side here is just a simple version of what I'm going to show you with the FET simulation, which I'll show you in the next video. And I've also put together a practical video in the lab just to show you how this works. So it's not a case of just taking my word for it. So we can increase our EMF firstly by increasing the number of coils. Let's increase the amount of conductors going through the magnetic field at any one time. So instead of using one wire, I'll use two wires. Those two wires, as they move together, will combine their um, magnet's field, which means I get an increase in number of field lines. Increase in number of field lines means more interaction means more force means more push means more electrons down this end, and then we get more repulsion, which is going to allow a greater current. Secondly, we can increase the strength of the magnet just by changing or buying a different magnet. The result is we can increase the number of field lines or decrease the number of field lines. Excuse me. This allows us to get a greater interaction between those two field lines, again enhancing the amount of force which is generated. The final thing we can do is increase the speed. Obviously, if I'm going slowly through the magnetic field, the result is I've only got a charge moving incredibly slowly, which means only a small amount of field is going to be generated. If I move it fast, the result is I get a huge amount of magnetic field which is generated. So that's more field lines, more interaction, more force. So slow, few field lines, not much force is generated because there's not much interaction. Fast, lots and lots of field lines. As a result, I get lots and lots of force, which means I get more push. Now this can all be put together in an algorithm, and basically this algorithm is EMF equals BLV, where EMF is the voltage, B is the magnetic field strength in Tesla, L is the length of the conductor which is going to be interacting within the magnetic field, and that's measured in meters, and V is going to be the velocity in meters per second. Now, this has also been linked together with the work done by Weber, and Faraday came up with another algorithm which was change in flux over time will also generate EMF. Time being principal here, obviously, the faster it's moving. If it moves from one place to the next over a shorter amount of time, we're actually going to get a larger EMF. Remember, flux was the field lines, or the density of the field lines, and flux can actually be determined by using BA, which is the field strength or the field density, and the area of the conductor which is present inside that field density. So as we move from one field density to another field density with a certain amount of time, basically we've got an EMF. And that makes sense if you think about it, because we're moving, it's the same sort of principle, but instead of talking about just moving from our conductor through the magnet, we're actually working on the idea that it's not uniform, the magnetic field. We've actually got a density. So if you're using this on the end of a bar magnet, remember a bar magnet basically has its field lines close at the beginning and then spread apart the further away. So as you move a bar magnet through, the result is you're going to get a change in flux density. Deal with that over time, and that's going to determine your EMF. So we came up with the formula EMF equals the change, or delta psi, of flux divided by the change in time, or delta t, where EMF is our voltage in volts, delta psi is our change in magnetic flux in Webers, and delta t is going to be our change in time in seconds. So here I've got a quick scenario to sort of try and explain it. Here I've got a bar magnet, and you can see the field lines are generated. Now you can see right at the beginning that right close to the magnet we've got lots and lots of field lines. So let's call that A. So I'm taking area A being that square. Now basically as I move it to B, which is this square, it's same area, but you will notice that at A I've got 1, 2, 3, 4, 5, 6. I've got about 7 field lines in that area. When I move it to B, I've only got probably two, maybe 3 field lines that's going to cover. So I go from 7 down to 3. Now the speed at which I do that will determine my EMF. Also the density of field lines, the more dense those field lines, going from very dense to less dense, is actually going to mean I'm going to get more EMF which is generated. So basically going from A to B will produce my change in flux, and as a result a voltage will be produced. Okay, so let's have a go at a couple of questions. So here I've got a diagram which shows a conductor of length 50 centimeters moving at right angles to a magnetic field directed out of the page. Notice there are dots there. If the magnetic field strength is 5.6 millitesla and the conductor is moving at a velocity of 4.5 meters per second across the flux lines, calculate the induced EMF across conductor AB and the direction of the current in the galvanometer circuit AGB. So I'm going from AGB. So let's work through what we've got. We know that EMF equals BLV. So we know that B is going to be 5.6 millitesla, so that's 5.6 times 10 to the negative 3 Tesla. I know that my length of my rod is 50 centimeters, which needs to be converted into meters, so it's 0.5 meters. And I also know that the speed at which I'm moving is 4.5 meters per second. So follow that through and I end up with a voltage of 1.26 times 10 to the negative 2 volts. So the second question asks us to calculate determine the direction of the current flow in the galvanometer circuit A going through the galvanometer all the way through to B. So basically in this case we know that our current is going to be flowing from positive to negative in this case. So basically the conventional current will flow from A through B and from A through G all the way through to B, or anti-clockwise around the external circuit. Now in this case we would use our right hand slap rule because we're talking about conventional current in this case, so we're going from positive through to negative. So as a result, what we would be showing is that we're coming down and pushing from the positive end all the way through if we're using conventional current. If we were using the idea of the actual flow of electrons, then what that would mean is that we would use our left-hand rule. So remember we've got this problem where electrons initially thought were to be positively charged. So a lot of the textbooks work on conventional current, i.e. we're moving from positive to negative. So you need to stipulate whether you're working with natural flow or conventional flow of current, just so that there is a good understanding as to how to work. So conventional current would basically state I'm coming down the page with my movement and my fingers are coming out of the page with my magnetic field. So we're pushing from A through to B, which is basically from positive to negative. But if we wanted to work out where the electrons were, the electrons actually would end up at B. So B would be your negative end, A would be your positive end. As a result, we flow conventionally positive to negative. Okay, so let's look at our second example. In this case, we've got a coil of rectangular wire, 12 centimeters by 6 centimeters, moving through a magnetic field generated by a stationary magnet. It moves from a field strength of 0.34 Tesla to a field of 0.57 Tesla. First question is going to ask us, is the coil moving towards or away from the magnet, and explain your reasoning? And what is the induced voltage that is produced if this happens in 3 milliseconds? Well, the first one states that it's moving towards the magnet as the field strength is getting stronger, meaning that the magnetic flux is increasing. So we're going from 0.34 to 0.57 Tesla, I think it is. So because our field strength is getting stronger, it means that the lines are getting denser, which means we're getting closer to that, to the magnet end. We're not moving away from the magnet. Because it is moving, the result is we are going to get an EMF. Okay, secondly, it's asked us to calculate what that EMF is. So we need to work out the change in flux over the change in time. Now, change in flux is the change in magnetic field strength. The area stays constant. So we can work out our change in magnetic field strength, because it's any change in is magnetic field strength final minus magnetic field strength initial, or BF minus BI. So it's 0.57, which is my final field strength, going to my initial field strength, 0.34 Tesla, and we end up with 0.23 Tesla. Then got to calculate my area and convert it all into meters. So it's 0.12 times 0.06 gives me 0.0072 meters squared. I then need to work out my change in flux, or delta psi, which basically is the field strength times the area, or change in field strength times the area. And so it's 0.23 times 0.0072 gives me 0.0017. Then I've obviously got to divide that by the change in time. Time is in 3 milliseconds, or 3 times 10 to the negative 3 seconds. So I divide 0.017 by 3 times 10 to the negative 3, and I get a voltage of 0.55 volts. Okay, well, I hope you found that useful. Alright, so check out the next video where I'm going to be using a simulation of FET just to demonstrate this production of EMF, and also check out the practical video which shows this working in reality. Well, thank you for joining me. I look forward to you meeting me again.